This video is going to look at section 1.12 acids and bases of AQA A-level chemistry, specifically looking at pH curves and indicators. This video will cover a brief recap of Year 1 A-level titrations, an introduction to pH curves, sometimes called titration curves, shapes of pH curves for different combinations of chemicals, describing titrations, and also indicators and how to select them for a specific titration. So titrations are a really important technique in chemistry. They're covered extensively in Year 1, and they're actually a required practical in Year 1, and then a required practical in Year 2 related to this topic. A titration is a quantitative analytical technique which is used to accurately determine the concentrations of chemicals. The main piece of equipment used is a burette, shown here to the right. Now, this is obviously only a diagram, but basically a burette is a long graduated cylinder, and graduated just means that it has these lines like a measuring cylinder does, with a tap at the bottom. The tap is able to be turned and allow solution to flow out, and the end of the burette has a very small opening, and that is to enable tiny drops, single drops, to be added to a solution, and we're going to look at that in just a second. So when we set up a titration, the normal way of doing this is that a solution of known concentration, where we know what the concentration is, which we refer to as the titrant, is placed in the burette. Now we'd use a funnel for that, and we need to make sure that we have the burette and funnel below eye level, never filling above your eye level in case you spill. And so we place the titrant in the burette. Now we use the solution of known concentration in the burette because you don't know what the volume will be. So you have a known concentration, but you'll get an unknown volume. Now also at the top of this solution, you need to notice that we have a curve in the surface that is known as a meniscus. Now the meniscus is where there is surface tension in the solution, which causes it to cling to the sides of that tube, and because you have a very narrow tube, that curve is quite pronounced. Now it's really important that you view at eye level as well, and lots of burettes will actually have lines that go all the way across the burette so that you can see if you're looking at eye level. And when I say across, I mean actually all around the burette. So if you're looking at eye level, you would just see a line. If you were looking above or below, you would see a ring as that mark for 2 centimeters cubed or whatever you were looking at. So eye level is extremely important. So once you've got your titrant in the burette, we would then put a set volume, which is normally 25 centimeters cubed, measured with a pipette, of a solution of unknown concentration, sometimes called the analyte, and that is placed in a conical flask under the burette. So as I said, 25 centimeters cubed is normal, and this time we have an unknown concentration, and that's because we know the volume. So you always make sure that in a titration, when you've got your 2 solutions, you know something about one of them. So you should know the volume if you don't know the concentration, and if you're using the burette and having an unknown volume, you would make sure you know the concentration, and that's just the standard. And it doesn't mean it's always that way, but that's normally what we'd do. So I'm going to put the 25 centimeters cubed in the conical flask. We then add an indicator to the analyte. The analyte is what we're analysing, so it's in the conical flask. And the indicator is specifically chosen to match the combination of the titrant and the analyte. So you cannot use the same indicator all the time. It depends on what reagents you're using, what combination of acid and base, for example. Now we would not use universal indicator for a titration. You need to have an indicator that only goes a combination of 2 colours. So for example, here I've got methyl orange. Methyl orange is a very common and very useful, and we're going to look at that later today, but a very common and very useful indicator for any type of acid-base titration. And what we can see here is actually we've got pink and yellow. It's not orange at all when we're looking at the two acid and base forms of this. So in alkali it is yellow. I meant to write alkali there, not yellow. So in alkali it is yellow, and in acid it's a sort of reddy pink colour. So I'm going to put some indicator into my analyte in the conical flask, and we can see here it's gone a pink colour. So if we look at the two colours of methyl orange, you should be able to work out that we've got an acid in this conical flask. Now as we perform the titration, that will change colour. So looking at the equipment we've got set up, would we be ready, or are we ready to start the titration as I have it set up just here? Can you spot any issues with my equipment? Okay, so I've just moved the equipment over just there. So looking at this, there are actually two main errors on this diagram. So there are a couple of errors that we can see here. And the first one is that the funnel should be removed as soon as it's finished being used. So as soon as you've poured the titrant into your burette, you should take that funnel out. If you leave the funnel in, residue can drip down from the funnel into the solution in the burette, and it will change the volume. And if you were in the middle of a titration, that would be a real issue. Now the second problem that we've got here is that the jet space, which is underneath the tap, should be filled with the titrant. Now that is very, very important. So I'm just going to put a little waste beaker underneath my burette here, and I'm going to open the tap just until that jet space is filled, and then you would discard the waste in the beaker. If that jet space isn't filled initially, when you open the tap to start the titration, the volume will go down on the burette. So the volume would go down at the top just here without any solution coming out of the bottom of the flask. So no solution will be added to the flask, and that will make the titer appear larger than it is. Now the word titer just means portion added from the burette. So the volume that you would measure would be called a titer. So just put the conical flask back there and we'll move on. So steps for performing a titration. This is a very brief overview of how you'd perform a titration. There are lots of other things you'd need to consider in terms of setting up the burette. You need to make sure that you're rinsing equipment and all that kind of stuff. But this is an extremely brief overview just as a reminder. So first of all, the first thing you do once you're set up is that you would conduct a rough run. You'd open the tap and add titrant from the burette while swirling the analyte in the conical flask until the indicator changes colour. Now this does not need to be accurate. It is literally open the tap, swirl the conical flask, and as soon as you see the colour change in the indicator, you turn the tap off. And it's just to give you an idea of whereabouts in terms of volume your colour change will happen. If you do it very slowly and do it drop rise from the beginning, if you're ending up needing having a titer that's nearly 50 centimeters cubed, you'll be there for a very long time. So we'll do the rough run, open the tap, and as soon as it changes colour, we turn that tap off. And so this is a rough run measured from the bottom of the meniscus, and you would record that on a table. Next step, we need to refresh the analyte and the indicator in the conical flask, which you would need to clean. So you'd tip away the yellow solution that we've got currently, rinse out that flask well with distilled water, and put another 25 centimeters cubed of the analyte and add some indicator. We'd then need to refill the burette if necessary. Now, if we look at the burette that we've got just here, this has used, if we were to count this up, that would be, this is a very poor diagram, but that would be 10 centimeters cubed roughly. But if you look here, you've only got 6 centimeters cubed of solution left in the burette that's measurable. So we would need to refill the burette just here because there wouldn't be enough in the burette to do another run. So just going to do that. There we go. Filled the burette up and we've refreshed the analyte. We've got it back to being red again. Now that we've done that, we start to conduct our proper runs where we're being accurate. So number 3, Add titrant to the flask, stopping 1 to 2 centimeters cubed from the volume of the rough run. So you literally open the tap and you just let solution run out to just 1.5 maybe centimeters cubed from your rough run value. Then you give the conical flask a good swirl, make sure that is completely mixed, and then we add titrant dropwise from this point, swirling after each drop. The end point is the point at which one drop, just a single drop, causes the indicator to change colour, and we're looking for the tiniest colour change. So I've just put here 2 little pictures of the conical flask with the indicator as it is currently. So we've got the starting colour, and then I've also just put here an image of the conical flask if we end up adding an excess of the titrant. So we have the 2 colours that we're looking for here. Now we're looking for the first point at which the colour is different from what it starts off as. As soon as it is different from that, then that is our end point, and we're looking for the single drop that makes it different from that. So I'm going to add 1 drop, give it a good swirl, nothing's happened. Add another drop, give it a swirl, still no change. Add another drop, swirl, no change. And then add a drop, and we can see here that we have the tiniest difference in colour. It's not gone yellow, but it is no longer the red that it started off with. Okay, so that we would be looking at as the end point, but we are talking about single drops. It is a tiny amount, and we're going to look at why that is so important in this video. So here's an example of what the results table would look like. We can see here that we've got the rough run labelled. That's the one where we just poured out or run out as much solution as needed to change the colour. Now the rough run is never used for any type of calculation because it is rough, it's not accurate. The other thing to notice is that the final volume is listed first. So if you were filling in this table, you would be putting your values in the initial volume first. And the reason for that is that it makes it a lot easier to then calculate the tighter volume or the volume that you've added, because you're doing the final volume of that value minus the initial volume, and it just makes it easier for doing the arithmetic. Everything on this table is recorded to 2 decimal places, and that is a standard for titrations. And you'll also notice that at the end, the final digit is always either a 0 or a 5. Now that's because burettes generally are able to measure to 1 decimal place. Okay, so there's a line for every 0.1, 0.2, 0.3, 0.4. And you'll either be looking at your meniscus measuring, if we were to do a very much a zoom in, the meniscus will either be on the line or it will be between 2 lines. Now, if it's on the line, we would say that that is 0.0. And if it is between the, not 0.00, sorry, and if it's between the lines, we would say that that is 0.05. So you can't be any more accurate than either being between or on the line. If it was ever so close to the line, you would say that, although it's not on the line, we would say that that is, we'd read that to be on the line. So now that we've been through that, we're going to have a look at a task 1, analysing titration results. So this is a year 1 calculation, as you would get in a year 1 paper. A titration was performed to determine the concentration of a solution of NaOH. 25 centimetre cubed aliquots of the NaOH were titrated with a 0.40 mole per decimetre cubed solution of HCl, and the following results were obtained. Calculate the concentration of the NaOH solution. Now, first of all, just to mention, the word aliquot just means portions, so that's a set amount. So 25 centimetres cubed goes into the conical flask. That's just referred to as an aliquot. Now, if you are a bit confused about this question, okay, in just a second, I'm going to say the video will pause, but if you're a bit confused with how to start, unpause the video, and then I'm going to give you a few hints. I'm going to break down that question. So don't worry if you get a little bit stuck when you pause the video for the first time. Just press play and I'll go through the stages of what to do. But have a go with the video being paused just for a second now. Have a think through the question. If you can do it, great. If you can't, press play again. So as I said, if you're a little bit confused of how to approach the question, I'm going to give you some steps. If you could do the question and you've got an answer, just make sure that your steps follow mine. So to calculate the concentration of the NaOH solution, first of all, A, calculate the average titer of the HCl. B, use your answer to A to calculate the moles of HCl. C, hence deduce the moles of NaOH. You will need to consider the stoichiometry. And D, calculate the concentration of the NaOH. So see if those little hints, those little steps help you at all. Pause the video again and then the answers will follow. Okay, task 1 answers. So a titration was performed to determine the concentration of a solution of NaOH. 25 centimetre cubed aliquots of the NaOH were titrated with a 0.4 mole per decimetre cubed solution of HCl, and the following results were obtained. So the table is showing us volumes of HCl. So I'll put that in green just to go with the fact that we have the concentration of HCl just here. We have been told a volume of NaOH that we are using, and it is asking us to calculate the concentration of the NaOH. So we need to be thinking about equations. So moles equals concentration times volume, or concentration equals moles over volume, however you want to remember that. But those are the equations we're going to be looking at because we've got volumes and concentrations. So we have got a concentration and we have volumes of HCl, so we should be able to do something with that. But the volumes of HCl we've been given are in this table, and we have 4 volumes of HCl. So we have 4 runs just here. So we need to think which volume are we going to use. Well, first of all, we're not going to be using the rough run straight away because it is rough. So you never include that in a calculation. And that leaves us with 3 runs to then look at. 19.65, 19.50, 19.40. Well, when it comes to titrations, we're looking for the concordant results. And concordant results are those that are in agreement with each other. And that means within 0.1 centimetres cubed of each other. And if we look, we have 19.50 and 19.45 that are within 0.05 of each other. So those two are the concordant results. So I'm going to work out the average titer, and the average titer is literally just the mean average of the 2 concordant results. So 19.50 plus 19.45 divided by 2, and so our average titer is 19.48 centimetres cubed. Now, because all the data in the table is to 2 dp, my average is also to 2 dp. So that's the first thing that we're looking at. Now, depending on the exam question, you might get 1 or 2 marks for that. More than likely in a year 2 paper, you'd get 1 mark for that, selecting the concordant titers and working out the average. So now that we've got the volume of HCl, which is what we've just worked out here, so that's the volume of HCl, and the question gave us the concentration of HCl, we can therefore work out moles of HCl, and that will be the concentration times the volume. The concentration in the question is 0.40 because it tells us I've highlighted that in green, and the volume we've just calculated is 19.48, and we need to divide that by 1,000 as always, because we need to make sure that we use decimeters cubed, because concentration is moles per decimeter cubed. Now when you put that into your calculator, that comes out to be 7.792 times 10 to the minus 3 moles. Then the next thing to consider is the stoichiometry. We know how many moles of HCl we've got, but we now need to know how many moles of NaOH that reacted with. In a titration, we are trying to get a neutralized solution. That's what the end point of the reaction gets us to when we've got a neutralization. And so we're looking for equimolar portions. So we need to think about the balanced equation, and NaCl reacts with NaOH in a 1-to-1 ratio to form NaCl and H2O. So we have a 1-to-1 reaction just here. So that means that the moles of HCl are going to be equal to the moles of NaOH. And therefore, the moles of NaOH that were in our 25 centimeters cubed is going to be 7.792 times 10 to the minus 3, just the same as the HCl. Now we know the volume that I've highlighted in yellow of sodium hydroxide was 25 centimeters cubed, and we've worked out how many moles there were, so we can now work out the concentration of NaOH as the question is asking us, and that will be the moles divided by the volume, both of HCl, 7.792 times 10 to the minus 3 divided by 25 over 1,000, again putting it in decimeters cubed, and that gives us a concentration of 0.31 mole per decimeter cubed. Now, I've put that to two significant figures because the data in the question was all to two significant figures. And if we just have a think about that concentration, the concentration is just slightly lower than the concentration of HCl, but that makes sense because the volume needed for sodium hydroxide was slightly greater, 25 centimeters cubed compared to 19.48. So moving on to look at pH curves now that we had a bit of a recap of titrations. The equipment that we use for a titration can be used or adapted to produce a pH curve. So instead of indicator being added to the analytes in the flask, a digital pH probe is placed in the flask instead and used to measure the change in pH as the titrant is added until the titrant is in excess. So we go past the end point of the reaction and we keep adding and we record the data. Now this is a picture of a very basic pH probe, and we literally just stick that in the conical flask at the same time as we're adding solution. Now this is a required practical for year 2, so it's important to understand how to do this, but obviously difficult to imagine what you're doing unless you do it actually in a practical situation. So I've got here a basic graph, and this is a graph of the pH of the reaction mixture in the conical flask against the volume of titrant added from the burette. Now, because we are measuring the pH, that goes on the y-axis, and because we're controlling the volume added, that goes on the x-axis. So just make sure that you get those around the right way, dependent and independent variables on the right axes. So if we then were to look at an example in terms of data, we would get a curve that looks like this. Now pH curves always form these S curves. Sometimes they have more than one dip or rise in it, so they can go backwards. But we're just going to look at standard pH curves for monoprotic and monobasic substances here. And you can see that in this case it starts off very high and ends up very low. And we have this straight part in the middle, and that's very important to look at. So just looking at that on a bigger scale, you can see here it starts off with a very high pH. Now, when we have a high pH, that obviously means that we have a strong base here. So this is starting off just for this particular example with a strong base because it has a very high pH. And if we were looking at the indicators, and I'm sticking with methyl orange as I started with earlier, methyl orange would be yellow at the beginning of this titration. Now, you would keep your pH probe in and you'd add small amounts, small volumes, swirling each time, and then writing down what the pH is on the pH meter. Now, you can do this with a data logger where it continually measures the pH. Normally, you'd be adding 2 centimeters cubed, measuring the pH, add another 2 centimeters cubed. And then as you notice the pH starting to change, so around here, you'll start noticing it going down a bit more, you would then start making the volumes added smaller. So you might add 0.5 centimeters cubed, just to make sure that you get a very clear curve. Now, the other end of the curve, we have a very low pH, and this is a pH of around 0.5. So this is actually a very strong acid here. And if we were doing this as a titration, then we would see the methyl orange go into the pink, the excess colour when we've got an acid. Now, if we were doing this with an indicator, we would normally stop when we get to the end point of the reaction, which we've already talked about is the point at which the colour change of the indicator occurs, where you would stop the reaction, literally the end point of the titration. And that would happen some point in the middle. Now, the end point is when the colour changes. It doesn't necessarily mean that that is the exact point where you've got the same amount of moles of your acid and base. That can be worked out from this graph. So if we look at this graph, we can see that there is this straight portion of the graph, which on this one on the screen is from about there to there where I've put those blue lines. That's the straight part of the graph. In fact, I'm just going to shift that bottom bit down. I'm going to put it around here. So that straight part of the graph, that's where the line is vertical. And that is showing the point at which one single drop causes the reaction mixture to tip from having an excess of base at the top here to having an excess of acid. And you can see that that one tiny drop causes a massive change in pH, a really rapid decrease. Now, if you think about the fact that pH is a log 10 scale, so pH 1 is 10 times different to pH 2, and if you think about how many H plus ions would be in one drop of an acid, it might give you an idea of why one tiny drop makes such a difference to the pH. And this also shows you how it's so easy to miss the end point in your reaction as well. Anyway, what we've got here is we've got this straight part of the graph. And if we were to go to the very midpoint of that, which on this graph is pH 7, this is a really important value or really important point, and it's known as the equivalence point. Now that is the point at which you do have equimolar portions of the acid and base in your reaction mixture. Now it is not necessarily going to be the end point. The end point will be anywhere from the bottom to the top of that straight part of the graph. And it doesn't really matter whereabouts the end point is, because you'll still get the same volume. If you were to read the volume down, you would still end up with the same equivalence volume that you read off your graph. So it doesn't really matter if the end point and equivalence point are not exactly the same, but the equivalence point is important to be aware of. And as I said, it is that point where it is the middle of the straight part of the graph. And we can read off the equivalence volume, so that's the volume of acid added to neutralise the base in this case. And we can also look at the pH at equivalence, which won't always be pH 7. That depends on the substances you start and end with. But for this particular graph, does end up being pH 7. So just to go over those pH key terms for the curves again, we had endpoint and we had equivalence point. Just have a think, can you remember what those two were and what the difference is between them? So the end point is the point at which the indicator changes colour. It's the point at which where you finish the titration, where you stop. And then the equivalence point is when two solutions have mixed together in equation proportions. So if you've got sodium chloride and HCl, you've got a 1-to-1 ratio, you've got the same number of moles of each. And this is the midpoint of the straight part of a titration curve. As I said, they are not the same, although they are related to each other. Now just a little note here, the term neutral point should not be used. And that's because some reactions are not neutral when they reach equivalence point. For example, the reaction between ammonia, NH3, and hydrochloric acid, HCl. Now, when we reach equivalence point here, that's the point at which we've got NH4 plus and Cl minus having been formed. So NH4Cl, although in aqueous solution it would split into the ions. Now, if you remember about what neutral means that the concentration of H plus is equal to the concentration of OH minus, and that won't always be the case for substances, just like NH3 and HCl. If you've mixed together 1 mole of each of these substances, you're not going to have a neutral solution because H plus and OH minus will not be equal to each other. So a quick note about describing titrations, and this is just about sentences that we can use to describe the process that's happening in a titration. So titrations can be described in the following format. Titrate X with Y. This could be an instruction that you're given. Titrate hydrochloric acid with sodium hydroxide. In this case, X is in the flask, or the analyte, and Y is in the burette, the titrant. You would be titrating with Y. Titrate with Y, because Y is the substance that's coming out of the burette. It would be Y that would be the titrant, it would be Y that would produce the titer, the volume, coming out of the burette. So when you're titrating with Y, you're physically turning the tap and allowing Y to come out of the burette. Another way of describing a titration could be a strong acid, strong base titration. So they performed a strong acid, strong base titration. In this example, or these examples, the first chemical, in this case the acid, is in the flask, and the second chemical is in the burette. That's actually true for both of these examples. In each case, the first chemical, in the top one it's X and in the bottom one it's acid, that's the thing that's in the flask in each case. So for the example we were just looking at, the pH is very high at the start. Therefore, the substance being measured in the conical flask that has the pH probe in it is a strong base, and a strong acid is being added because it ends up being acidic. So we're starting off with a base and we're ending up with an acid. So this is described as titrated a strong base with a strong acid. Started off with the strong base, ended up with a strong acid. Or we could say a strong base, strong acid titration. In each case, the word base is first because it is first on the pH chart and it's what we start with in the conical flask. Moving on to look at the shapes of pH curve in a bit more detail. There are a number of pH curves that you need to know the shapes of and also the corresponding pHs. Now, as I've said already, this one that we've looked at is a strong base at the top and a strong acid at the bottom. So this purple curve is a strong base, strong acid titration and could be referred to as a strong base, strong acid curve. Now, if we change the chemicals, the curve shape will change as well. So I'm adding on here a blue line, and if we look, we can see here that we've got still a strong acid at the bottom. So still ending up with a very low pH, that's still a strong acid. However, we've got at the top, we can see a lower pH that it starts off with. So it starts off around pH 11 instead of the pH 13 or so. So this is actually starting off with a weak base instead of the strong base. But because we're still ending up with a strong acid, this would be a weak base, strong acid titration. Not able to write today for some reason. So strong acid titration. So those are those two. Now we're going to write down and have a closer look at the shapes in just a second. Now back to the strong base, strong acid titration again, just to compare them. If we change the acid this time, okay, so this time I'm keeping the strong base, but now I'm adding a different acid. So starting off still with a strong base. What we can see at the bottom here is that the pH, it ends up being a lot higher. And that ends up at around 2.5, which corresponds to a weak acid. So here we have titrated a strong base with a weak acid. Now, the other thing just to notice is that we do have this sort of little dip here at the bottom. Now, that's sort of indicative of a weak acid. You sort of always get that extra little dip. And when we look at the weak acid strong base curve, you'll see that in a little bit more detail. So looking at these shapes just a bit more, you need to make sure you write these down so that you've got the shapes recorded. What we're going to do is have a look at the pHs of the equivalence points and also the pHs that they start and end at, and the pH where the straight part starts and finishes. So this first graph just here is one that we've already looked at. We start off with a pH of approximately pH 1 at the bottom. So we have a pH 1 just here, and it ends around pH 13 or 14. It ends up being very, very high. Now, the straight part of this graph goes from around pH 10 to around pH 4 approximately, and you do need to know that. And then we have an equivalence point in the center of pH 7. So this particular graph, because it starts off with a low pH of pH 1, this one is a strong acid, strong base titration curve or pH curve. The mirror image that we've looked at already with the shape going that way round would be a strong base, strong acid, and the values would be in exactly the same place, just flipped round. And as I said, you do need to know start and end pHs, and you do need to know those values where the straight part of the graph starts and ends, 10 and 4, and then it has a pH equivalence of about 7. Now the next graph we're going to have a look at here is this blue one, and it is again mirror image of one we've looked at already. And again, it starts off with a pH of about 1, which means that we're starting off with a strong acid. But we're ending up with a pH of about 10 or 11, which means that we're ending up with a weak base. Now this time the straight part of the graph is going from around pH 8 this time, so it's a bit lower because it's a weak base, but it's still going down to be around pH 4. Now the equivalence point is in the middle of those two, and so for this one we'd have an equivalence of around pH 6. As long as it is less than 7, that would be right for this one. Our next example, okay, we are starting with a slightly higher pH. You can see here it starts at around pH 2, and we're ending up at around pH 13. So we're starting off with a weak acid and ending up with a strong base for this one. The equivalence point ranges here. So the straight part of the graph is now starting at around 6 and ending at around 10. So that straight part has shifted up a bit. And that means that the equivalence point is at around pH 8. Now, as long as you know that the pH equivalence is above 7, then that would be fine for that one. Final graph that we're going to look at on this slide is this one. Now we're starting off with a pH of around 2 and we're ending up with a pH of around 11. So the pH of 2 means that we are starting off with a weak acid, not wear acid, and we're ending up with a weak base because it is around pH 11. Now what you should notice here is that there is no vertical part of the graph. There is no bit of that graph that goes straight up or straight down. So that means that there is no value that we can work out for equivalence. You cannot determine equivalence point for a weak acid, weak base, or weak base, weak acid titration using a titration curve. So we would just leave that. So task 2, shapes of pH curve. Time for you to have a go. First task, match the pH curves with the correct description. So there are 3 pH curves, and is each one of them a strong base, weak acid, strong base, strong acid, or strong acid, weak base? And the number 2, sketch pH curves for the following. You must include the pH values on the y-axis. A titration of ammonia with hydrochloric acid. B, a titration of nitric acid with sodium hydroxide. And C, a titration of ethanoic acid with ammonia. Pause the video and then mark your answers. So task 2 answers. Number 1, match the pH curves with the correct description. So there are our pH curves, and the options I gave you are just there on screen. So this first one we have here starts at a pH of around 13, which means that we're starting with a strong base. And we're ending up with a pH of around 1, which means we're ending up with a strong acid. So this one is going to be that middle option there, strong base, strong acid. The next graph, we are starting at pH of around 1, which means that we have a strong acid. And we're ending up at around pH 10 or 11, so that is a weak base. Now we can also see here that it's not quite so much of a sharp curve, it's kind of a bit more gradual, that curve there. But that one being a strong acid, weak base means that it is that final answer just there. And our final graph, we start with a pH of 13, so we have a strong base. We also have a very defined curve here, so almost not quite a right angle, but nearly. Whereas we end up with a pH of around 2, and we have this more gradual curve, and then that dip at the bottom, which means that we have a weak acid. So strong base, weak acid would be that first option. Apologies, you can hear my pipes going for our central heating. Number 2, sketch pH curves for the following. You must include the pH values on the y-axis. Well, I've put the pH values in just here. So we have a titration of ammonia, which is a weak base, with hydrochloric acid, which is a strong acid. So weak bases are going to be around 10 or around 11-ish on the pH, and the strong acid is going to be around pH 1. And we're doing the titration of ammonia with the hydrochloric acid. That means that we're adding the hydrochloric acid. So that means that we're starting at around pH 11 and we're ending up at around pH 1. And our equivalence point, or the straight part of the graph, is going to be from around pH 8 to around pH 4. So we're going to add that in. I'm going to put that straight part of the graph in just there. And so we've got a weak base, a gradual curve, and then we have a strong acid, so we're going to have quite a distinct curve at the bottom like that. For part B, we've got nitric acid, which is a strong acid being titrated with sodium hydroxide, which is a strong base. So the nitric acid is going to start around pH 1 and the sodium hydroxide finish around 13 or 14. And because we're doing the titration with the sodium hydroxide, we're going to end up at a higher pH, and we're titrating the nitric acid, so we're starting off with that. And for a strong base, strong acid, whichever way around we're looking at, we would have the straight part of the graph being from around 4 to around 10. So I'm going to put that in first. That's the straight part of the graph. And so we're going to have quite a distinct, clear bend, not gradual, either end, and that will be what the curve looks like. Final one here, we've got a titration of ethanoic acid, which is a weak acid with ammonia, which is a weak base. We're titrating with the ammonia, which is weak, and therefore we'll end up with a pH of around 11. We're starting off with the ethanoic acid, that's first, so we're going to start off with a pH of around 2. And there's going to be no equivalence point that we can determine in the middle. This is going to be just a sort of fairly smooth S-curve that looks a bit like that. Might be better off to have it a little bit more of an S, but there will be no vertical part of that graph. And moving on to indicators, the final part of this video. Indicators are all weak acids which have a different colour to their conjugate base. Now remember, the conjugate base is formed when the weak acid donates its proton. So here we have just an example equilibrium reaction, HIN referring to the weak acid. We've got an H here because that can be donated, and the IN just refers to the rest of the molecule. That dissociates into H plus and the IN minus, and it is in equilibrium. And we've got two different colour forms. We've got colour 1 and colour 2, and that's really important. You need colours for an indicator, otherwise it's very difficult to use. So in a low pH environment with a high concentration of H+, if we apply Le Chatelier's principle and say we've got a high amount of H+, in what direction will the equilibrium shift? Well, the equilibrium is going to shift to get rid of or remove a high concentration of H+. So in a low pH environment with a high concentration of H+, the equilibrium will move left and cause colour 1 to be seen. Now in a solution with a high pH that has a low concentration of H+, the equilibrium will shift to produce H+. And therefore equilibrium is shifted to the right and we would see colour 2. Now, two common indicators that are used at A-level are methyl orange, that I've already talked about, and phenolphthalein, sometimes called phenolphthalein. Very strange spelling there. PHTH, that is not me making a mistake, that is how it's spelt. These two indicators can be used for most A-level titrations. And if we look at the colours, we have here methyl orange that we've already looked at, that is a reddy colour in acid, yellow in alkali, and then the end point you'd be looking at for the titration is the orange in the middle. Really handy with these with methyl orange to see if you've gone too far left or right. If it's pink or pinky red or yellow, you've missed your end point completely. And the colour change range that occurs over is between 3.2 and 4.4. So that end point colour that we would see occurs in that pH range. Now phenolphthalein is colourless in acid and pink in alkali, sort of pinky purple. Now depending on what way you're going for a titration, if you were going from acid to alkali, the end point is the first permanent hint of pink, and you can see this middle picture here, it's barely pink at all. So difficult to get that one, difficult to judge the same every time, but it is that tiniest hint of pink that you'd be looking for. That colour change occurs in the range of 8.2 to 10. And those colour change ranges are really important. We're going to look at why just now. For an indicator to work for a titration, the whole of the colour change range for the indicator must sit within the range on the graph where the pH changes rapidly, i.e. the straight part of the graph. So just have a look at this graph, just another example here. We have here a strong acid, strong base curve, because it starts off with a low pH for a strong acid, ends up with a strong base. And if we look at phenolphthalein, it has a range of 8.2 to 10. And if I just overlay that range on the graph, we can see that the whole of that range, the whole of that block, fits over or sits over the straight part of the graph. And that means that we would be getting a colour change where that one drop causes the pH to shoot up in this case. If we look at methyl orange with a pH range of 3.2 to 4.4, excusing my dodgy diagram, we'll just imagine that that is straight, that colour change also occurs and sits over that straight part of the graph. And so we would be getting a colour change when we add one drop. We would see that very, very clearly. Now, if I just change the graph there and we now look at titration with a weak acid, so we're starting off here with a weak acid. If we were doing this titration, the colour change of the indicator would happen at this volume, because that is where the curve hits that active range of the methyl orange. And you'll see that that is quite a bit different to the equivalence volume, which means that we would get an incorrect endpoint. The endpoint would be that red volume that I've listed on the bottom, and that would be too low compared to the equivalence volume. So it just shows you that it is quite important to make sure you pick the right indicator. So what do you need to remember for this topic then? For this part of the topic, you must know the shapes of the graphs for all combinations of acids and bases, both strong and weak. Now, I showed you 4 on the screen, but you need to remember the mirror image ones. So there are actually 8 shapes, but as I said, you can argue that there's only 4 and mirror images. You need to know the approximate pH values for the equivalence points and straight parts of the graphs for each. So all of those pH labels I put on the y-axis, you need to make sure you know. And you also have to be able to select a suitable indicator for a titration, which is what we just looked at. It would also be very sensible to ensure that you know the names, colour changes and active pH range of both methyl orange and phenolphthalein. Quite commonly asked in the A-level exams is suggest a suitable indicator for a titration between ammonia and hydrochloric acid. Having methyl orange and phenolphthalein as ones that you know is just very, very useful. You don't need to remember a whole list. Those two are enough. You could be given a table to select an indicator from, but you definitely need to make sure that you know those two. Okay, task 3, going to give you an exam style question. Number 1, sketch a pH curve for the reaction that occurs when 50 centimeters cubed of 0.2 mole per decimeter cubed HCl is added to 25 centimeters cubed of a solution of 0.1 mole per decimeter cubed NH3, and that's 4 marks. Just giving you the grid there so you've got something to sort of aim at. It does only need to be a sketch graph. Number 2, choose a suitable indicator that could be used for this titration from the table and state the colour change that would be observed. 2 marks. And there's the table just with the information. As always, pause the video, have a go, and then mark your answers. Okay, so answers to task 3. Number 1, sketch a pH curve for the reaction that occurs when 50 centimeters cubed of 0.2 molar HCl is added to 25 centimeters cubed of 0.1 mole per decimeter cubed NH3. And as I said, we're looking at this being a full mark question. So we need to read through the question again and think like a chemist, as I always say. So think like a chemist. What chemicals do we have? Well, first of all, we've got HCl, which is a strong acid, and that means that on the graph it will be around pH 1. And then we have ammonia, which is a weak base, and so we'd be looking at a pH of around 11. Now, because we are adding the HCl is added, we are starting off with the ammonia, and we're ending up with the HCl. So this is a weak base, strong acid curve. So we're going to be starting at around pH 11, and it's going to be ending up at around pH 1. Now, if we think about the equivalence point here and where that will be, the straight part of the graph will be with the equivalence point in the middle. But it's going to be going from around pH 8 to around pH 4 with an equivalence point of around pH 6 in the middle just there. So that already is loads of information, and we could just draw a graph in and say Right, done. But they've given us more information for this particular question. They've given us concentrations and volumes. So we need to think about what that tells us and what we can do with this. And what it means is that they are wanting us to actually ensure that the equivalence volume is correct on this as well. Now, because we're ending up with the acid, it's the acid that's in excess. And that means our limiting reagent, and this is all tying together with year 1 calculations, our limiting reagent is the ammonia. So it's the ammonia that is going to tell us all of the information that we need. And we've been given a volume and a concentration of ammonia. And if we have volume and concentration, we can work out moles. So I'm going to do that. Moles of ammonia is the concentration times the volume. Concentration is 0.1 times 25 over 1,000. Make sure those centimetres cubed are in decimeters cubed. And so therefore we have 2.5 times 10 to the minus 3 moles of ammonia. Now we want to know the volume of acid added, because that is what is on the x-axis of the curve. So we've got to use our moles of ammonia to work out volume of acid. Now NH3 has a lone pair on the N and reacts in a 1-to-1 ratio, as we've already looked at, to form NH4 plus and Cl minus. So this is 1-to-1. So the moles of HCl is the same as the moles of ammonia, 2.5 times 10 to the minus 3. Therefore, the volume of HCl is going to be moles over concentration, 2.5 times 10 to the minus 3 moles, divided by the concentration, which the question tells us is 0.2. And that comes out to be 0.00, oh, sorry, too many noughts, 0.0125, but that's decimeters cubed. And the graph is centimeters cubed, so we need to times by 1,000, 12.5 centimeters cubed. So we would need to be putting the straight part of the graph just around there. So at 12.5 and between 8 and 4. So if we add the rest of the curve in, it wasn't very good, let's do that again. Something like that. Okay. And that would be the 4 marks. So we'll be looking at the pHs that we're starting and finishing, the volume of equivalence. There might be a mark for some of the working, but if you drew that curve with those values in the right place, then you would be looking at 4 marks. If you didn't work out the equivalence volume, and if you did the first graph that I mentioned with the equivalence point just sort of somewhere in the middle, then you'd be looking at maybe 2 out of 4. I'll just put a neater version of that in there. So answer for 2, choose a suitable indicator that could be used for this titration from the table and state the colour change that would be observed. So we need to look at the graph that's just been drawn, and we're looking for the fact that the sharp change, that rapid change in pH, is from around 8 to around 4, so we're looking for an indicator that would fit in that range. So if we start off with the trapeolin, I'm not sure if that's how you say it, but we'll go with that. That has a pH range of 1.3 to 3. So if I put that in here, that would be around there. Now, we would get a pH change after the end point, so the volume would be incorrect for that one. So we would not want to use the trapeolin for that one. Just put that value back in. If we look at bromo cresol green, I'll keep the colours, we have an active range here of 3.8 to 5.4, so that would be around here. That looks like it could be likely. And then if we go for the cresol purple and have a look at that, we have a range of 7.6 to 9.2. Now, if we look at the purple there, that wouldn't be any good because we'd be getting the colour change occurring at this volume, which is before the equivalence volume, which would be where I've just drawn that solid arrow in. So the correct one to choose would be the bromocresol green. So that would be 1 mark that we'd put as an answer. And then the colour change that we would see, we're looking here, the colours are yellow and blue. Now the colour in acid is yellow and the colour in alkali is blue, but we are starting with the alkali and ending with the acid. So the colour change would be blue to yellow. Now, one of the really common mistakes people make with these questions is they only give one colour. If you're asked for a colour change, then you do have to give the colour both before and after. So that is pH curves and indicators. Let me know if you've got any questions, and good luck.